Fluid Mechanics, Chapter 10, Pipe Flow. So in this particular lecture, we're going to discuss friction losses due to surface roughness. We'll take a look at the Mooney diagram, and we'll work several examples. So our lecture objectives for this chapter are to discuss the friction losses due to surface roughness within a pipe and describe how to use experimental data to determine these losses. We'll try to analyze and design pipe systems having various fittings and connections, and we'll explain some of the methods engineers use to measure flow through a pipe. So it all starts off reviewing what's known as the Reynolds number. So the Reynolds number came about in 1883 when Osborne Reynolds established a criterion for identifying laminar flow within a pipe. He did this by controlling the flow of water passing through a glass tube using an apparatus similar to the one shown below. Here, he used colored dye was injected into a stream at A, and he observed the flow through the pipe as it went out through B, as valve B was opened. What Osborne Reynolds observed was that for slow rates, the flow in the tube was observed to be laminar, since the dark streak remained straight and uniform. However, as the flow was increased by further opening the valve at B, the streak began to break down into and it would underwent what's known as a transitional flow. Finally, as the valve at B was opened further, what's known as turbulence occurred because the dye became fully dispersed throughout the water in the tube. So what is the difference between laminar and turbulent flow? Well, from Reynolds' experiments, he was able to classify the different flow regimes by using the following relationship that's now known as the Reynolds number. So the Reynolds number is a dimensionless quantity. It's calculated based on either using this equation or this equation. Rho is the density of the fluid. V is the velocity of fluid. D is the diameter of the pipe. Mu is the dynamic viscosity of the fluid. Nu is the kinetic viscosity of the fluid. So generally, the different flow regimes are classified as follows. For Reynolds numbers less than 2,000, that's referred to as laminar flow. For Reynolds numbers between 2,000 and 4,000, that's transitional flow. And for Reynolds numbers greater than 4,000, it's turbulent flow. So this particular chapter deals with frictional losses. So we look at frictional losses due to laminar flow and turbulent flow. So the friction loss within a pipe can be determined analytically for laminar flow. It's defined as the friction factor F and is given by the following formula. It's just 64 divided by the Reynolds number. This term F is known as the Darcy friction factor. Or here in this chapter, we simply call it the friction factor. For laminar flow, it can be seen only as a function of the Reynolds number. Once the friction factor is determined, we can calculate what's known as the major head loss by using what's known as the Darcy-Wabash equation, shown below. So F is the number here, based on the Reynolds number. L and D are the length and diameter of the pipe, B is the velocity, and G is the acceleration due to gravity. Rather than using the Moody diagram to determine the friction factor for turbulent flow, we can also use the results obtained by empirical formulas. So these are basically just formulas that are fit to the curves. First is what's known as the Colebrook transcendental equation. So this is a transcendental equation, so this literally has to be solved numerically, either using MATLAB or some programming language. There's another one that's a close approximation to the Colebrook equation. This is a Halin approximation, and it gives results within 2%. So again, this F is the friction factor. Little epsilon, the little eta here is the relative roughness. D is the pipe diameter, and you got the Reynolds number. So let's take a look at example 10.1 on how to apply this. So we have a 6-inch diameter galvanized iron pipe shown below, transports water at a temperature of 100 degrees Fahrenheit. Determine the head loss and pressure drop in 200 feet of the pipe if the flow is given by Q equals 400 gallons per minute. So first we need to go to Appendix A, and we can look up the relative constants. At 100 degrees Fahrenheit, the density of water is 1.927 slugs per cubic feet, and the velocity is volume flow rate is 7.39 times 10 to the minus 6 square feet per second. So here, I've simply went along. There's a plot back in Appendix A of temperature versus all these different parameters. So you can kind of look these up. So here is the density, and here is the kinematic of viscosity. So to classify the flow, we have to actually calculate the Reynolds number now. So V is Q divided by A, so we can convert 400 gallons per minute and then divide by the area. Let's put everything in foot-pound system. We calculate it to be 4.539 feet per second. So we can calculate the Reynolds number. We can get the kinematic viscosity from in the previous slide. So we get 3.07 times 10 to the fifth. So this is turbulent, since we're greater than 2300. So continuing on with example 10.1. So the value of the roughness constant is eta is taken from the table on the top of the Moody diagram on the inside back cover. For galvanized iron pipe, we get 0.0005. So using that value, the relative roughness, which is epsilon over eta over d, is 0.0005 divided by 0.5 feet. That's the length of our pipe. We get 0.0001. So using this value for the relative roughness and the Reynolds number that we calculated, 3.04 times 10 to the fifth, we can go into our Moody diagram. So here we can find epsilon over d, which is 0.000. It's 0.0010. So here, let me get a pencil here. So here's our value here. So we follow this blue line all the way over until it intercepts with 3.04 times 10 to the fifth. Well, the closest we can do here is to get the 3, right? So if you come straight up from the 3 to where those intercept, you get here, roughly here. Then if you come all the way over to the left-hand side, to me, I get about 0.021, somewhere about here. Now the book says you get 0.0208. There's no way you can read that off this chart. But we'll take his value that he got and continue using it. Now, if instead you want to use the Halin equation, you can plug in the value for a relative roughness and a Reynolds number. You calculate, you get 0.0205. So that's pretty close to the previous value. And to be consistent, what the book does is he uses the value from the Moody diagram to calculate the major loss. So he plugs in the values, he gets 2.66 feet is the major loss, HL. Let's continue on. Let's look at example 10.2. Here we have heavy oil flowing through 3 kilometers of cast iron pipe having a diameter of 250 millimeters. If the volumetric flow rate is 40 liters per second, determine the head loss in the pipe. Take the kinematic viscosity of oil to be 0.12 times 10 to the minus 3 meters squared per second. So first, let's calculate the Reynolds number. We can calculate the velocity. If we can calculate the Reynolds number, we get 1698. Since that's less than 2300, this is laminar flow. So things become a little easier. So therefore, the friction factor is 64 over the Reynolds number is 0.0377. The major head loss is given by the following equation. So plugging in the parameters we get 15.3 meters. So here, in this case, the head loss is the consequence of the oil's viscosity, and it doesn't really depend on the roughness, surface roughness of the pipe. Example 10.3. So we have a fan shown is used to force air having a temperature of 60 degrees Fahrenheit through the 8-inch diameter pipe. It's a galvanized sheet metal duct. Determine the required power output of the fan if the length of the duct is 200 feet and the flow is to be 240 cubic feet per minute. Take the roughness factor to be 0.0005 feet. So we can go to Appendix A and we can calculate for air at 60 degrees Fahrenheit. We can calculate the density. And we can calculate we can look up the kinematic viscosities. So continue with those values we found from the previous slide. We can calculate the velocity. We can calculate the Reynolds number. And notice the Reynolds number here is greater than 2300, so this is turbulent flow. So here we can calculate the relative roughness. It's the epsilon value divided by 8 inches divided by 12 converts it. So this 8 inches divided by 12 converts that diameter to a feet. So it's 0.00075. So using this value, then the Reynolds number, the Moody diagram, you can look at the Moody diagram, you get 0.0235, roughly. So here's a chart of the Moody diagram for this problem. So again, we calculate the relative roughness, and we got a value of 0.00075, and the Reynolds number 4.84 times 10 to the fourth. So coming along a chart, 4.84 times 10 to the fourth, let's call that roughly 5. So we're somewhere in here, let's say. And the 0.00075, we're somewhere in here. So we can come over, follow these lines roughly to about there, and then come straight over and read off what the friction factor is. You get roughly 0.0235, but again, if you pick the value of 0.024 or 0.023, that's pretty close. So here once we find what the friction factor is, we can calculate the major head loss. We get 14.375 feet. So finally, to calculate the head loss of the fan, we're going to select a control volume that includes the fan, the duct, and a portion of the still air on the inlet side. For this case, the pressure in and the pressure out are both going to be 0. And since it's atmospheric, Vn is approximately 0. So using the Bernoulli equation on the input and output, this term is 0, this term is 0. Since it's along the center line, Zn is 0 and Z out is 0. There's no turbine, so that term is 0. The head loss of the pipe we calculated in the previous slide is 14.375. What else we got here? Pressure out 0. V out, V squared out over 2. We know what the V value was. We were told that in the problem. So the only thing we don't know is the fan, H of the fan, which we can calculate to 16.414 feet. So finally, we can calculate the power output of the fan. It's given by the following equation. gamma Q times H of the fan. So gamma, we looked up in Appendix A, it's the density, 0.00237. This is our G value. So those two together is the gamma. Q we calculated in the previous slide. 240 cubic feet per minute are 4 cubic feet per second. And the H of the fan is 16.414 feet. So there we calculate the power output and convert these to horsepower. We get 0.00911 horsepower.